coming to this workshop also you had an exposure of SPSS. At least you have heard about this particular package and how it works. Today and over the last next two sessions, say today and tomorrow, we will be focusing on one of the interdependence technique called factor analysis. When it is to be used, how it is to be used, and how the results can be interpreted, and what are the outputs that are to be included in your papers while you are writing certain journal papers, or what are the outputs that are to be included in your PhD thesis. Now, before starting this particular session, I would like to share a few, you can say, anxieties of the scholar when we interact with them. As they often say, they don't get access to SPSS. SPSS is a proprietary software, as you well know. It's not an open source kind of a thing. And it is very costly, very costly. Our university purchased SPSS with only 4 modules and an added IBM SPSS Amos. The 4-module SPSS, it costs around 13 lakhs to 13.5 lakhs, and SPSS Amos another 6.5 lakhs. So it is, knowing the fact that SPSS actually is having 25 or 26 modules, we only could purchase only 4 with that much of money. So at times it becomes very difficult for the scholars as well as for many teachers, as most of the universities and colleges, they do not have access to the licensed version of SPSS. So we prefer a very undesirable way to access SPSS. Now, to get rid of this, I can actually share with you one of the software that is available free of cost. It's an open source software. If you can download, it will actually replicate the operations of SPSS in a nice way. Most of the statistical computations can be done on this platform. It is called it is almost an anagram to SPSS. It is called Pspp. I will show you the comparative, graphical outputs or the layouts of these two software. You have already seen SPSS. Now we will have a chance to see the Pspp also. Only one thing that can inhibit you a little bit in using Pspp is the layout. It's almost like a black and white, almost like someone using a DOS base of operating system some time back. So it is almost a black. It doesn't, have that kind of a colored interface or multicolored interface like SPSS, or rather than smart kind of an outlook. But it will do the same kind of analysis, and it will give you the same kind of output. As a matter of fact, we who are engaged actively in social science research, particularly in management, economics, sociology, anthropology, all the allied and related co-disciplinary areas, we often use these days more advanced kind of a software which goes beyond SPSS, because SPSS has certain limitations. So we have switched off to smart PLS with regard to certain analysis. We have switched to Adanco with regard to certain kind of analysis. So all these software programs or application tools you can use simultaneously. It's not that for a particular operation or a particular statistical procedure you have to depend only on SPSS. Then we have the Jamovi, which is an online tool which gives you a real-time data analysis opportunity. You can use that too. So there are a lot of you can say different varieties of tools which you can use. And one who knows how to use RStudio or the Python program, they can also do anything that can be done on the SPSS platform. Now, as far as today's session and tomorrow's sessions are concerned, we will be focusing on, as I have told you, factor analysis, which is segregated into two parts. But today we will focus on the exploratory part, the EFA, the exploratory factor analysis. And tomorrow we will concentrate on the confirmatory part, or the confirmatory factor analysis. As the name suggests, in case of EFA, there is an exploration. So we do not reach to any kind of a conclusion, or there is very little scope for data validation or reliability check, etc., etc. So there is no conformity as far as the output of EFAs are concerned. So only if you put the data in under the CFA, or the confirmatory factor analysis, then we can have certain idea about the validity and the reliability issues of the output. So what we will do, we will take a very close look into the EFA. Then we will go on for the hands-on, because you need to know certain basics about the EFA, how the data is managed, or what kind of data requirement is there, under which circumstances a particular researcher will feel free to use the factor analysis, and how do you check, how will you be absolutely sure that whether the data that you have collected is amenable to for factor analysis, amenable to factor analysis or not. That means whether the data that you have collected, whether it is apt or quite fit to conduct a factor analysis. And one of the most important thing is to check the sample adequacy, whether the data that you have collected is indicative enough of sample adequacy, whether adequate sample has been collected that represent the entire data set. So if you can say, one of you, whether the screen is visible, if any one of you can confirm.
Yes, sir.
Yes, sir, visible.
Yes, sir, visible.
Okay, so as I've told you that it will be basically today we will be focusing on the EFA part. Now, before going into this particular presentation, let me just tell you that while going through these kind of sessions, particularly for data analysis, use of softwares, etc., most of the scholars, since they are coming from different kinds of background, different kinds of you can say exposure of very to a different degree of exposure to mathematics and statistics, etc. A number of scholars may have this kind of inhibition or a confusion whether they need to learn the details of statistics or mathematics before approaching for this application part or use of any software for application. Actually, you see, when we are working for different different domains, like the domains of the social science or domains of science or engineering or literature, etc., in most of the cases, particularly in social science, we are more or less focusing on the applied part. Since the social science, it brings or it converges a lot of discipline together, so the people or the scholars or the researchers who are coming in this particular domain and focusing or taking up any research area, they are not we are not likely to get people only from the mathematics background or from the statistical background. So they have a very compromised kind of a knowledge about maths and stat. So when you are dealing a research project or a PhD in social science area, you need to understand one thing, that I will be using certain mathematical applications or statistical applications as an application only by understanding the fact that how it actually justifies or rationalizes or support my research objective. So if I am intended to find something and if it is very specific, how can how can a particular statistical procedure will help me achieving that. In most of the cases in social science, we will be constructing certain hypotheses based on our literature review, based on our gap analysis, identification of variables. We assume certain dependency, we assume certain kind of construct measurement, etc. And we represent it by virtue of constructing certain working hypotheses, and those hypotheses are to be tested. So our selection of statistical tool or our selection of statistical process will be apt if that particular working hypothesis can be tested in a very robust manner by using all those statistical applications. Definitely one thing is to be understood. If I am applying a particular statistical process to test my hypothesis, or to find out a relationship between variables, or to predict one variable, or to just analyze a particular data set, I need to know why I am using that particular test. Or what does this test is supposed to provide me in terms of output, number one. And number two, whether the data that I have collected, whether this data support this kind of test to be undertaken. Suppose there can be, a particular researcher can have access or is accessing, say, a nominal data or a ordinal data or a scale data. So all different kinds of statistical procedure cannot be applied across these different kind of data set. So there has to be a perfect match between the kind of data. If you are having a nominal data, what kind of applications you can take up. If you are having categorical variables, ordinal data, what kind of statistical applications you can take up. Or if you are having scale data, like you have collected data with the help of interval scale, like a Likert scale, or even a ratio scale, what kind of statistical applications is apt or is fit to conduct or to assess that or analyze that particular data set. These things becomes very important. So you need to know about that particular analysis, what this analysis is supposed to bring out. So we start from there. So in statistical analysis, particularly in multivariate techniques, we classify the multivariate techniques into the dependence method and the interdependence method. So the dependence method, we can just put a very simple definition or a simple understanding or concept for this. The multivariate technique appropriate when one or more of the variables can be identified as dependent variables and the remaining as independent variables. This is the the most common kind of analysis most of the researchers come up with. So we have a number of dependence technique that we can apply. We have regression analysis, we have the multiple regression analysis, we have the logistic regression analysis, we have the hierarchical regression analysis, then we have the ridge and lasso regression analysis, we have the conjoint analysis, the canonical correlation, discriminant analysis, which uses the categorical variable and thereby makes it different from that of regression analysis. We have MANOVA, we have the SEM, the structural equation modeling, which necessarily follows after the confirmatory factor analysis. So we have a number of dependence technique where we find existence of a very well and predefined set of dependent and independent variables. Whereas in case of an interdependence technique, this is also a multivariate statistical technique where the whole set of interdependent relationships is examined. So we are not getting the traditional or conventional kind of an arrangement that there will be a set of dependent, there will be a set of independent, when we would like to examine the relationship, either the strength of associationship between these two sets of variables, or the predictability of the dependent variable based on the independent variable. So no single variable is defined as either a dependent or an independent. The factor analysis comes under this particular technique. So analysis of all variables in the data set, it takes place simultaneously. And the goal of the major objective is data summarization or group things together to minimize the number of variables, or to summarize the data, to simplify the data. Normally it takes place when a particular researcher has to deal with a huge data set with a great number of variables. So no one variable is predicted or explained by the others. And what are the normal statistical process that we adopt for this interdependence techniques? The factor analysis is used, cluster analysis, whereby the clusters are identified based on the agglomeration process or agglomeration schedules. Then we have the perceptual mapping. Perceptual mapping is a very interesting thing, which is often used by the industry people or the marketers to identify where their brands are placed in terms of certain dimensions. Say in terms of price and quality, if I fix 2 dimensions, based on that, where their products or brands are being placed and how they are being perceived by the customers. So perceptual mapping is one such example of statistical application which is widely used in the industry, particularly by the corporate houses. Then we have the MDS technique, the multidimensional scaling. It is also an interdependence technique, and correspondence analysis, that is also an interdependence technique. So today we are basically focusing on the factor analysis, or more specifically, we are focusing on the exploratory part of the factor analysis. And since I have told you at the very beginning that we need to realize what kind of data we are collecting, what kind of variables we are having in our hand, and depending on that, we will be selecting which stream or which course of action, statistical action, to be taken. It's almost like a patient visiting a doctor. A doctor is diagnosing the patient to find out or to mine out what kind of ailment or what kind of disease this person is suffering from, and then the treatment will follow that course. So the doctor is not making an abrupt choice or a very wild guess what the patient is suffering from. So the doctor goes for say multiple number of tests, and based on those tests the doctor fixes up a course of treatment. So in case of selecting particular statistical applications or a particular course of data analysis, you need to be very careful about what kind of data you are accessing, what kind of variable sets you are having, what is the objective of your research, what kind of hypothesis you have constructed, and based on that you progress. One thing is taken for granted when we are talking about this, that you are basically focusing on a quantitative research and not a qualitative research, because once we change the domain from quantitative to qualitative, the entire thing changes. So let us see the classification of the multivariate methods depending on the number of variables. This is represented with the help of a flow chart and the kind of data that you are accessing. So if the number of dependent variable is 1, obviously it gives you a hint that you should proceed for the dependence method. So if it is 1, even the number of dependent variable, it is 1, then you proceed for the dependence method. If it is none, on the right hand side, you can see you are proceeding for the interdependence methods. And you have the factor analysis and cluster analysis, perceptual mapping, MDS technique, correspondence analysis. All those statistical applications can be applied. Now, if you are going for the dependence method, then comes the nature of data. In case of dependence method, if it is a non-metric data, that means you have access to certain nominal data, you can go for discriminant analysis or conjoint analysis. If you are having ordinal kind of a data, you can go for rank correlation and all that. And if you are having interval or ratio data, which is a metric data, you can go for regression, ANOVA or MANOVA or conjoint analysis. So again, depending on what kind of data, you have to be sure about the kind of data that you have collected. and be sure about the spread of variables that you are having. If you have already predefined or pre-identified set of dependent and independent variables, then obviously the dependence method is the selection. Now the question is where independence methods are to be applied. Okay, one practical example is, say for example, a researcher is interested to develop a scale or to develop a measurement construct. Okay, there we are supposed to apply the interdependence method. Or there is an existing scale and the researcher is interested either to expand or to redefine or to reintroduce or to newly introduce certain kind of factors or dimensions in that particular scale. There also, you can go for the interdependence technique, because here while developing a scale or while developing a measurement instrument or while changing a little bit or modifying a little bit the existing measurement instrument, or rather I should say, if you want to contextualize a very well tested measurement instrument, you can use the interdependence method. Mostly when scale development, that is the most natural example that comes to our mind, that interdependence technique is applied in most of the cases where a researcher is very much interested or focused on developing a measurement instrument or a scale. So defining factor analysis is an interdependence technique whose primary purpose is to define the underlying structure among the variables in the analysis. Now, very closely related to factor analysis is another concept which is called the principal component analysis, or PCA. Probably you have heard about that also. Now, the back-end algorithm or the back-end calculations or statistical computations for both these analysis, or the approaches to both these analysis is almost similar, except the fact that principal component analysis, or PCA, primarily focuses on data reduction. It doesn't go to that extent to identify what is the underlying factor structure of my data set. So if I have a huge number of variables, suppose I am working with 50 to 60 variables, and I do not know whether those variables, they converge and they cluster, they group into certain kind of dimensions or factors, and whether all those variables ranging from 50 to 60, all those variables are very important part of the underlying factor structure. With the naked eye, it's almost impossible to assess. So we need to put it through a process which is called a factor analysis, particularly the EFA, to have certain understanding that which factors are very important or which factors are very significant for the factor structure that I am looking for, and what exactly is the nature of that particular factor structure. Okay, so that from that particular point of view, from data summarization or data reduction to identification of the factor structure that properly defines the data set at hand, the exploratory factor analysis is used. Now, as I have told you, under what circumstances? Number one, to identify the underlying dimensions or factors that explains the correlations among a set of variables. A very small example is provided over here. Say, for example, a set of personality trait statements may be used to measure the personality dimensions of the people. Say, for example, a particular person may be very introvert, but it's very difficult to measure introvertness directly. So we require certain surrogated variables or proxy variables to have an understanding about what introvertness or what extrovertness actually mean. Okay, so we normally identify a series of statements. Those statements are basically representative of either extrovert, observed variables, or observed or manifested kind of behavioral orientations, or representations or manifestations of of introvertness. So we have a series of statements, and across those statements, we normally use a scale. Based on that particular scale, normally it is an interval scale, the respondents are required to provide their ranking, and that ranking can range from 1 to 5 or 1 to 7, and we put the entire data set into this factor analysis process to identify which are the statements that converge into a single factor or into a single component. Then the researchers task is to name that particular component, which is a representative dimension of either extrovertness or introvertness. So those were those constructs or those issues which are very difficult to measure directly. Say a very popular scale was developed in 1985 to measure service quality. So service quality is an issue that was very difficult to measure directly, because there are so many issues, there are so many factors, so many dimensions of service quality. So there was a groundbreaking study taken up by three researchers, Leonard Berry, S. Parashuraman, and Valerie Zitham, in 1985. They identified initially 125 set of statements or 125 set of variables, because they were not sure how many variables will be actually retained by the final instrument. So they populated the initial instrument with 125 variables or statements, against which they collected response in a 1 to 7 point Likert scale. And when they put the entire data into an exploratory factor analysis, only 85 variables were retained. So out of 125, 40 variables got deleted simply because of the fact they did not show very significant factor loading. Okay, so they were insignificant as a result of this particular analysis. So 85 variables were written, and it was found that these 85 variables they could be grouped into 5 factors. Okay, so approximately there were a huge number of variables per factor. On an average, there was almost 17 variables per factor. Now, these 5 factors they identified, they named it. Suppose factor 1, they named it as reliability. Factor 2, they named it as tangibility. Factor 3, they named it as empathy. Factor 4, they named it as responsiveness. And factor 5, they named it as assurance. So they identified these 5 factors or 5 dimensions which can directly represent the quality of the service. And then they conducted several tests to check the robustness of this particular instrument. So they went ahead and checked the service quality of banking system. They checked the service quality of a hospitality service provider. They checked the service quality of the e-commerce service provider. And when they tried to check the service quality of the e-commerce service provider, they found that there can be certain additional service quality dimensions. So they changed the scale from service quality to e-service quality in the year 2004. So that's why I'm telling you that when you are either trying to develop a new instrument or trying to contextualize an existing instrument into a new context. Like, for example, service quality, when in 1985 and subsequently revised in 1988, subsequently revised in 1992, when initial service quality scales were formed, they did not take into consideration the electronic factor or the digital platform impact of the digital platform factor. So it's only in the middle of between 2010 and 2000, probably in 2004, 2003. They started, studying this, the automated banking system, the perception of the customers about the ATM machines or internet banking, etc., etc. And they found certain additional dimensions which can best explain the perceptual service quality. So it get contextualized to the digital platform. So this is one of the use. And the second one is to identify a new smaller set of uncorrelated variables to replace the original set of correlated variables. One of the issues that what kind of data set is amenable for factor analysis there should be very high degree of correlation between the variables which are used for the data analysis, actually factor analysis. So if you have 50 variables, or if you have 60 variables, or if you have 20 variables, 25 variables, there has to be a high degree of correlation between these variables. This is one of the preconditions to conduct a factor analysis. So there should be very high degree of correlation between the variables, but the factors that are coming out of this factor analysis, that means the underlying factor structure, say you are starting your factor analysis with say 40 variables, and after conducting the factor analysis, if you see that these 40 variables are loading into 5 different factors, say factor 1 to factor 5, these factors should be uncorrelated with each other. So we start with a highly correlated set of variables to identify the factors which are uncorrelated with each other. So in case of psychographic factors identification, for particularly by the industry or by the corporate houses, when they try to differentiate between customers who are very loyal for a particular brand, or customers who are non-loyal to a particular brand, these psychographic factors which are being identified, this can be one of the studies. The psychographic factors who are uncorrelated to each other, but responsible for identifying the difference between the loyal consumers and the non-loyal consumers. So the use of factor analysis is basically done to reduce the data, number one, to manage, to reduce the data within a manageable proportion, but to identify the significant variables which have significant factor loadings, and number two, to identify the factors on which these variables actually converge. So the underlying factor structure to be identified. We talked a little bit about the principal component analysis because, as I have told you, that the factors to correlate after the entire process is completed. So it uses an orthogonal transformation to convert a set of observations of possibly correlated variables. You try to understand what is written over here. Orthogonal transformation is used to produce a resultant group of factors which will be uncorrelated with each other. So it is used to convert a set of observations of possibly correlated variables. As I have told you, one of the prerequisites to conduct a factor analysis, that the variables are well correlated with each other, into a set of values of linearly uncorrelated variables, also known as the principal component. So we are identifying the factors which are uncorrelated with each other. Sometimes it is also known as the principal modes of variation. Now, mainly the PCA is used to explain the variance structure of a set of variables through linear combinations. It is often used as a dimensionality reduction technique. Normally, actually, PCA is only used for dimension reduction or the data reduction technique. So, technically, the difference between PCA and factor analysis is the aim of the PCA is to explain the variance, while the EFA explains the covariance between the variables. And when I say it explains the covariance between the variables, basically two random variables, or whether they change together or whether the changes in those two variables occur together. That means it can take you or lead you forward to have a measure between the correlationship between those two random variables. So that's the base. Yeah,
sir. Actually, you are saying that what I have not understood is we are taking correlated variables.
Yeah.
And then we are transforming into a linearly uncorrelated structure.
Factors. Yeah.
Factors.
Yes.
So I'm giving one example. Suppose for agricultural production, for agricultural credit,
Hmm.
We say what is agricultural credit, agricultural output. Say what are the
Hmm.
factors responsible? Maybe credit is one factor. Maybe land irrigation is one factor. So these are
Hmm.
all correlated factors we are taking.
Hmm.
Okay,
Hmm.
then we are with the related factors we are uh, putting in an uncorrelated structure.
Right. Right. So
Okay.
normally what happens, you see, when you are applying this factor analysis, because as I have told you that the one of the basic you can say applications of a factor analysis is while we are developing a particular scale or a measurement instrument, which in any case say it can be a new scale or a new measurement instrument, or when you are trying to modify an existing measurement instrument, or in other cases when you are having a number of observed variables and the number of observed variables is plenty. Say for example, you if you have that kind of a variable set or a data set whereby you do not have a predefined or pre-identified kind of a dependence and interdependence kind of a variable distribution, so that you cannot afford or you cannot adopt a dependence technique as a statistical process, there we are going for this interdependence technique. So in case of factor analysis, we start with the variables or the set of data or the set of variables or the set of statements in certain cases, or you will find in journal papers or in books it is also written as items. Okay, because when you are designing a particular scale, one of the preliminary activities that the researcher has to undertake is item generation. Item generation basically is nothing, is to identify the statements which will best describe that particular scale. So when we are generating items, item is basically generated from either pre-existing literature, or you are designing your own items which will best explain the kind of measurement construct you want to design. So when we are constructing this particular scale, initially we generate a lot of item which are very closely, which are supposed to be very closely interrelated with or correlated with each other. And at the end of the data analysis, at the end of the factor analysis, we are supposed to find a linear combination of these variables, which will result in certain independent factors which will be uncorrelated with each other. And that will be the underlying factor structure of your entire data set. That exactly what we are aiming for EFA. Hope I have answered your question.
Mm, oh, yes, sir.
Okay, the moment we take up one example hands-on, probably you can understand it in a better way. Okay.
Okay, sir.
So just moving forward, when you are designing your analysis for EFA, that means when you are creating a situation that so that you can conduct an EFA, there are certain general requirements. We call it a prerequisite of EFA. So what are the general requirements? One of the preliminary requirements is the type of scale. So the observed variables should be measured in either interval or ratio scale, or at least at the ordinal level. So we are talking about a metric kind of a data which is amenable or which is suitable for the factor analysis. Now, the number of items. So if the researcher has a priori knowledge about the underlying factor structure and want to test the dimensionality, then at least 5 or more variables should be included to represent each factor structure. So if you have certain knowledge about the factor structure, that this particular phenomena, or this particular you can say component, or this particular issue can be well measured with the help of these 4 dimensions or these 5 factors, then at least if it is a 5-factor structure you are anticipating, or if you are anticipating a 6-factor structure, if it is a 5-factor structure, you should have at least 25 variables, 5 variables per structure. It is just a rule of thumb, right? It's not that something which is very specific in nature. It may increase. But at least 5 or more variables should be included to represent each factor structure. Now, tomorrow when we will, focus on the confirmatory factor analysis, you will find that for a latent variable means the variables which cannot be observed, which cannot be directly measured. And the measurement of those variables again depends on certain observed variables. So how many observed variables are required? What is the exact number, or what is the range of number of the observed variables that aptly represents or measures the latent construct? That we will try to understand with the help of a matrix structure. Then the sample size. Again, the rule of the thumb for sample size is to have at least 5 times as many cases as variables entered into the factor analysis plus 10. Now, to make it very robust, the sample size should be 10:1. So for every one item, there has to be 10 samples. So if you have, say, for example, a particular researcher is having, say, 25 set of variables. So the minimum number of respondent which is required, the sample size that is to be required, will be 250. Otherwise, in the sample adequacy test, there is a test in the factor analysis which is called the Kmo test, the Kaiser-Meyer-Olkin test, that gives out an output, and the benchmarked output or a reference output is anything over 0.7 is to be accepted as an indicator for a sample adequacy. So anything below 5.5, that means your sample is not adequate to conduct the factor analysis. So what is the rule of thumb? Suppose you have 30 variables, you need to have a minimum of 300 sample size. You have 20 variables, you need to have a minimum of 200 sample size. So unit is to item. So for every item, 10 units, the sample unit size should be 10. So one item means one variable. I have used the term item because when you are, actually constructing a scale, for the scale, the unit of the scale is basically, we are calling them item, because the item generation is the very preliminary activity for constructing a particular scale. So number of items will determine actually what will be your sample size. So that is the normal or the convention, that for every item you require 10 number of respondent. What are the statistical, those are the general assumptions as far as the EFA is concerned. So you need to have either a ratio scale or an interval scale, or at least an ordinal level measurement as far as the data is concerned. The number of items, it again depends on whether the particular researcher is having certain kind of prior knowledge about the factor structure. In most of the cases, when you are going for a new scale development, your initial knowledge or prior knowledge of factor structure almost will be absent, unless it is very well supported by the extant literature, whereby you can get certain understanding about what will be the approximate factors, or the likely factors or dimensions of this particular scale under construction. Sample size, which is very important, as I have told you, that it will depend on how many variables you are dealing with. So you can easily now imagine, if a particular researcher is having say more than 50 variables, then obviously the study will be very huge, because it requires a huge sample size to conduct that particular study, to make the study at least very robust in nature. Now, what are the statistical assumptions for this EFA to be conducted? Random sampling is one of the requirements, but what we have seen in general, that when we are going for field work, for collection of samples, in most of the cases, the researchers are opting for convenience sampling, which is again a non-probability kind of a sampling. You see, there is almost a forceful imposition of that kind of sampling technique on EFA these days. That should be avoided. Probability sampling is the ideal case for the EFA or any kind of factor analysis. If you are going for a very non-probability kind of sampling, convenience sampling, purposive, judgmental, etc., that is not very suitable for conducting an EFA. But we are seeing PhD work, so we are seeing journal papers even where the convenience sampling process has been taken up and the data has been put forward for factor analysis. Linearity is another assumption. Relationship between all observed variables is linear. That is an assumption. And the normal distribution. Each pair of the observed variables should display a bivariate normal distribution. So the scatter plot that you will get should be elliptical in nature. And variables should be metric. And that we have also understood from the general assumption when we said that the type of scale should be either interval or ratio, or at least there should be ordinal variables. Then conceptual assumptions are there in terms of variable selection and sample homogeneity. When it comes to variable selection, factor analysis is based on the basic assumption that there exists an underlying structure for the selected set of variables. So the presence of high correlation and subsequent interpretation do not guarantee relevance, even if it meets the statistical assumptions. So it is the researcher's responsibility to select the set of variables or items that are conceptually very valid and appropriate to represent the underlying dimension. Now, what does this particular portion suggest? That you need to be very thorough with your literature review, and the variables that you are identifying, if that has to be conceptually valid, it must have the support of a very good literature and appropriate to represent the underlying dimension. Sample homogeneity, the selected sample should be homogeneous with respect to the underlying factor structure. What does it mean? Suppose if there is demographic heterogeneity, for example, I'm just citing one example. If there is a demographic heterogeneity, that means, say, in the sample you have male and female both, and in the sample you have different age groups, and in the sample maybe you are having different disposable income. So if there are three demographic factors which are heterogeneous in nature, probably it will have an impact on the overall output. Because for male and female, we have often seen that the resultant output, it will be very difficult to interpret, and it will be very difficult to extrapolate on a specific kind of a demographic spread. So if you have male and if you have male and female, and if you want to create a homogeneity in the sample, then you can fix up this demographic variables, and you can fix up the ranges. So if you are focusing on, say, one particular gender, say for females, you can fix up the age range, you can fix up the occupational area, you can fix up the disposable income range, etc., to make to identify a homogeneous subset of sample from a very heterogeneous distribution. So sample homogeneity is one of the conceptual assumptions. So when we put data into factor analysis process, we assume that sample homogeneity is maintained. Now, there are certain deriving factors for assessing, overall fit or the number of factor extracted. There are four specific, criterion that are to be satisfied. One is the latent truth criterion. You see the latent truth criterion, priori criterion, percentage of variance. Latent truth and percentage of variance criterion, these two are almost similar in nature. So the percentage of variance, the total variance explained, is one of the indicators of the overall fit, or the number of factors that has been identified. Normally it is graphically represented with this Cree test criterion. So the percentage of variance, how many factors is explaining the maximum variance, and how many factors are extracted. If it is graphically plotted, we get this Cree plot. Okay, so once we take up the hands-on, you will see how this Cree plot is coming up. This is the decision-making process by and factor analysis. We have already discussed it. Concept of rotation. Yes, this is very much important. One of the issues in let me just explain it a little bit. One of the issues in factor analysis is the concept of rotation. Now, the concept of rotation basically crops up as a result of or to ensure the unidimensionality. Now, this will be very much clear once we take up a practical example. You will find what is exactly meant by rotation. Let me take the example first, then I will just explain. Otherwise, it will be difficult. Anything else, or we will directly move on? Yeah. Reporting for EFA outputs and interpretation. You see, these days, if you see good journal papers, the journal papers which are coming out from the reputed houses, initially we had a trend that the EFA results are very explicitly mentioned. Okay. Now, EFA results should be explicitly mentioned if you are stopping at the exploratory part only. If you are proceeding for CFA, that means confirmatory factor analysis, and subsequently if you are again undertaking, if you are switching for from interdependence technique to the dependence technique, that means from CFA you are going to structural equation model by identifying dependent and independent variables by virtue of conducting the CFA. You need not go for explicit representation of EFA outputs. Okay, but as I have told you, if you are restricting yourself in identifying the the measurement constructs only, or identifying the factor structure, or identifying the dimensional spread, or the number of variables which adequately describes a particular scale or constitute a particular scale, then go for explicit output. Normally, correlation matrix is one of the output. You have to give the determinant, mention the determinant. The Bartlett's test of sphericity and Kmo measure, you have to report for that. Kmo measure, as I have told you, it's basically talks about the sample adequacy. So there are certain reference values, and you have certain cited reference. You can go for Nunali and Bernstein of 1974, who has stated, or Black and Hare. So there are a number of references you can get over internet. So what is the Kmo measure figure? So normally anything over 0.7 is accepted, but we tend to cite Kmo measure or Kmo output, which is greater than 0.8. In most of the papers, you will find that acceptable Kmo measure, or for confirming the sample adequacy, is more than 0.8. Bartlett's test of sphericity actually tests the null hypothesis, and it rejects the null hypothesis that that the correlation matrix is either an identity matrix or a singular matrix. Okay, so it again is dependent on what the determinant value. So if the off diagonal matrix of a correlation, if it becomes 0, that means absolutely no correlation between the variable. Lack of correlation between each and every variable, then the number of factor that will be extracted, it will be equal to the number of variables. So no correlationship between the variable will result in the exact number of factor that is of the variables. So 20 variables uncorrelated with each other will produce 20 factors which will be uncorrelated with each other. So that's why we one of the assumption is, when we are taking a data set and putting it through a factor analysis process, we assume that the variables or the items of a scale are highly correlated with each other. Sometimes anti-image matrix is reported, but anti-image matrix is a mirror image of the correlation matrix with exactly opposite figures with same connotation. But sometimes it is reported, but anti-image matrix is not required for reporting in the journal paper. Communality, you just you can use a table in your in your PhD thesis. This communality, or the eigenvalues, the total variance explained, the scree plot, the component matrix, rotated component matrix, each and every of these output you can include in your thesis, in your PhD thesis, but definitely not in a journal paper. As I have told you, in the journal paper, the most used, or the most represented kind of output is the rotated component matrix, the KMO measure, the Bartlett's test of sphericity. The Bartlett test of sphericity is nothing but the chi-square value and the degrees of freedom. So these are the few things, and the correlation determinant is highlighted. So these are the few things which are to be used when you are reporting in a journal paper. If you are stopping after the EFA, but if you are proceeding and you are confirming the factor analysis by adopting a confirmatory factor analysis, whereby you are using the discriminant validity and the convergent validity and the nomological validity. So all the validation techniques are used for the initial factor structure. Then you need not go for a very extravagant reporting of your EFA output. There the reviewers of the paper will only focus on what is your output for the confirmatory factor analysis, and there the goodness of fit indices, etc., and the validity measures, that will be focused upon. And if you move one step forward, as I have told you, to take the CFA into a structural equation kind of a thing, so you can go for the structural equation model. There also you will find a number of things that can be represented, including the structural equation model itself in the form of the graphical plotting. So these are as far as the reporting of the outputs and interpretation of EFA is concerned. As I have told you, if I go one step forward to validate the factor analysis, I have to carry out the confirmatory factor analysis, and thereby I will check the convergent validity of the model, the discriminant validity of the model, and the nomological or the face validity. So while reporting, remember that in a thesis you can include everything in a PhD thesis, but when in a journal paper you can go for a very elaborate representation of EFA. One of the things that you need to measure or at least to represent is the common method bias, whether a single factor is responsible for the maximum variance. So if a single factor is responsible, then probably your factor structure does not hold good. That means it is not a very good kind of a factor structure. At least the data was not amenable. Initially, you thought the data was fit to conduct a factor analysis. Probably it was not fit after getting the common method bias. Normally, the common method bias does not crop up until and unless there is an issue of correlation between the variables, lack of correlation between the variables to start with. So this is all about the factor analysis, or a very aptly put, the exploratory factor analysis. Now let us take up an example and the hands-on using SPSS so that you can have an understanding how these things are the factor analysis is applied, or under what circumstances. So let us take a very small example, a very small data set we will be using. This is the example. This is a very random kind of an example, very arbitrary example. Consider a construction company, say for example, ABC Builders, that is planning to build an apartment complex near a university. Suppose the company is interested in identifying the perception of the university faculties regarding the value consciousness, price consciousness, and purchase decision involvement, and the sales proneness that would help the company to construct and design apartments according to the target people. Now, you see, to start with, this particular company has somehow identified 4 factors. Eventually, these 4 factors may be renamed or renomenclated after the factor analysis, but to start with, they have some kind of a concept. Now, as a researcher, you may ask this question: from where does this concept come? This concept will definitely emerge from the literature that you study. The literature with regard to your research objective and the research domain, the basic fundamental research questions that you have put forward, and the related literature review. If you study the literature, you will come to know about certain kind of factors. So it will give you certain idea about certain dimensions or certain factors. Even if it is not there, it's not a problem. But in this case, at least this particular builder is having certain preconceived notion about certain kind of existence of certain factors. So there are 4 factors or 4 dimensions they have already identified, but it is not a mandatory thing or not a hard and fast thing to stick with these factors after the analysis is carried out. So they have identified 4 factors, likely 4 factors: the value consciousness of the customers. In this case, the customers are the teachers. The price consciousness, because they are trying to sell them flat or certain kind of real estate. Price consciousness and purchase decision involvement, and sale proneness. Why they are doing this, or why they have considered these 4 factors? That would help the company to construct and design apartments according to their target people. Here, the target people are the teachers of the university. So the company hired a marketing research firm to determine how these 4 major response dimensions the faculty is concerned about before buying an apartment. So how these 4 factors they influence, or how these 4 factors the faculties are actually considering for buying an apartment. So the research firm identified the scale to measure these 4 constructs using some existing literature in price consciousness. So they created a 3-item, price consciousness scale, 3-item. They used a 5-point Likert scale to generate response. Value consciousness, again, 3-item. Sale proneness, 2-item, and PDI, 4-item. So how many variables are there? 3 plus 3, 6 plus 2 is 8 plus 4 is 12. So there are 12 variables to start with. So the minimum number of response that this particular factor analysis require is 60. 1:5. So for 1 item, there should be minimum 5 response, and to make the scale very robust and very dynamic, it should be 1:10. So for 12 items, there should be a minimum of, or say 100, there should be a maximum of 120. Okay. So say if we collect a response of say 90 to 90 to 100, or even up to 120, it will be quite good. So anything over 50, probably sample adequacy will be achieved. So here the firm surveyed 98 randomly selected respondents or faculties using different scales to determine the perception of the faculties with regard to the PDI. PDI means the purchase decision involvement, the price and value consciousness, and sale proneness. So this is the case, and I will show you the data set also. This is the data set. If I go to the variable view, you will find there are 12 variables because over here we have already said that value consciousness is measured with 3 item, price consciousness with 3 items, sell proneness with 2 items, and PDI with 4 items. So there has to be 3 plus 3 plus 2 plus 4, 12 variables. So 12 variables are, included in this particular data set. And if we go to the data view, you will find they have collected 98 responses. Okay, so 98, they have collected response from 98 teachers. So you know how to populate this particular variable view. This is a editable kind of a thing, so you can put the item over here. If you see the item, I can show you. These are the variables. These are the 12 variables. Say variable 1, they put it like this: selecting from many types of brands of this product, like apartments available in the market. Would you say that I would not care at all as to which one I buy? Would not care at all. It is given 1 to a maximum 5. I would care a great deal as to which one to buy. So if I care a great deal as to which one I buy, I will go for 5. And if I don't care at all, I can select any one without being very careful about which one I am buying, is 1. So I'm using a 5-point. This particular company is using a 5-point Likert scale or an interval scale to generate the response. So for every variable, they have fixed up this particular scale. So say, for example, how important would it be to you to make a right choice of this product from the ABC builders? Say not at all important is 1, and extremely important is 5, and there are certain intermediary level of agreeableness with regard to this thing. So in making your selection of this product from ABC builders, how concerned would you be the outcome of your choice? Not at all concerned is 1, very much concerned is 5. So this is the kind of scale, and these are the 12 variables that has been used. So when you will be doing SPSS analysis, all the items you can fit in over here. You can just copy paste from the Word file, or you can just type it out over here, all these labels, and you can fix up the values over here. So what does the value of 1 mean? What does the value of 1 mean? Say not concerned. Okay, so you can add, you can go for number 2. What does it mean? And say if I add the extreme one, number 5, extremely concerned. So in between these two, there are intermediary values, say 2, 3, and 4. So that can be included also over here. So for labeling and including the values for alignment, etc., you can use this variable editor view, and you can do it. As far as the data view is concerned, we have populated this particular spreadsheet with data. Now, as I have told you, that I will show you parallelly the software that is almost similar to that of SPSS, which you can use absolutely free of cost. Now, this is the Pspp interface. You see, in the Pspp interface also, you can get this kind of a view, this is the data view, and this is the variable view. So you see, there's not much of a difference, except the fact that it is a little bit unattractive because it is black and white. Unfortunately, it has not been, the colored version is not released yet. But you can do all those analysis, all those statistical procedures what SPSS does. So over here, when we are going for factor analysis, the first thing is we need to identify you see the scale reliability. Because we are actually designing scale. If you are designing a particular scale, the internal reliability of the scale can be identified by a value. It is called the Cronbach's alpha, or the alpha value. So there are a lot of citations about the reference score of alpha. So if it is over 0.8, it is considered to have, the scale is considered to have the internal reliability. So from where you can get this, scale reliability, you just scroll it down, you go to analyze, okay, and scroll it down to scale, and then go to reliability analysis, and you will see by default this alpha value will be taken. There are other modes of reliability analysis also, like split half and Gutman, etc. But normally for factor analysis we go for the Cronbach's alpha, and from variable 1 to variable 12 we just transfer it to the this particular item box, okay, and just click OK. So we are basically measuring the internal reliability of the data set. So the Cronbach's alpha score is 0.838, number of items is 12. Now, as I have told you, the reference or the benchmark of Cronbach alpha to accept it as a reliable data set is anything over 0.8. If it goes and touch 0.9, it's very good. So 0.838, probably we can go ahead and conduct the factor analysis. So again, you go to analyze. So what actually we are doing here, we are actually going for reduction of dimension, or the dimension reduction. So over here, you scroll down, you will get this dimension reduction, and dimension reduction, you choose this factor. Okay, it opens up a very small window. The first thing you have to do is to transfer all the variables into this variable box. So all the variables which are to be used for the factor analysis, in this case, there are 12 variables. So all the variables are being transferred to this variable box. And now comes the configuration of everything. So what we require in terms of output, because we need to interpret the output and include those interpretations in our results. And then we need to draw the conclusion. So for the descriptive, you see, you check the Kmo and Bartlett's test of sphericity. That is very important. You click the determinant. Okay, there will be an initial solution by default. Let it be like that. You go for coefficient and significance levels. See, if you are going for determinant by by default, it will produce the correlation table. But if you are, doing your work for the PhD thesis, probably you will require much more table or tabular support, the result support. So you can click for coefficients and the significance level of those coefficients. So continue. Extraction based on eigenvalues greater than 1. At least eigenvalues greater than 1, why this particular thing is used, or why eigenvalue is considered or should be there greater than 1, we will just explain that. And over here in the display, there will be unrotated factor solution. If you require only the rotated one, you can just unselect it, or you may keep it as unrotated factor solution will also be displayed. And this is the graphical representation we were talking about, the scree plot. So you can go for the scree plot also. Now, a maximum number of iterations for convergence is 25. So the algorithm will definitely decide this by default. So no need to disturb this. Let it be 25 only. So continue. Rotation. Now, rotation, go for varimax, because we want to maximize variance. That's you see, there are two different kind of rotation. One is rotation which is basically oblique rotation, and the second one is called the orthogonal rotation. Now in orthogonal rotation, it doesn't allow the factor to correlate. Okay, but in oblique rotation, it actually makes the factor correlate with each other. Now, as far as the orthogonal rotation is concerned, we have three processes. One is this varimax, the second one is this quantimax, and the third one is the equamax. So Varimax, Quantimax, and Equamax, these are the three processes of rotation which are orthogonal in nature. And there are two options for oblique rotation. One is called the direct oblimin, and the second one is called the Promax. Okay. Normally, when you are using a Promax, you are supposed to have a huge data set. So the industries or the corporate houses which are using huge data set, say customer data set of bank or from any other databases, they normally go for this kind of oblique rotation. So for most of the academic purposes, we go for this Varimax rotation. So we go for this continue. I will explain this concept of rotation as I have told you. Scores, no need to do anything with this. Of factors to be extracted. So everything is clear. So we have put forward the descriptives. We have specified the extraction process, what we need in terms of extraction. We have specified the rotation. We have not yet specified the options. Okay, so let us click OK. Okay, so this is the factor analysis, result. So the first thing that you need to report, as I have told you, determinant. Determinant which varies from 0 to 1. You can directly report this, which proves that it is neither a singular matrix or an identity matrix, this correlation matrix. As far as the Kmo's test is concerned, you see the Kmo is well over 0.7. Okay, so the sample adequacy is achieved. So there is no issue with the sampling. We have used 98 samples. As I have told you that there were 12 items or 12 variables, and we have understood that for each variable there should be a minimum of 5 responses, and to make the scale very robust there should be 10 responses. So we require a minimum of 50. We require a minimum of 60 in this particular case because there were 12 variables, and a maximum of 120 to make it very robust in nature. But we have obtained 98 responses, and we found that the sample is adequate enough to conduct the factor analysis. As far as the significance of the approximate chi-square by virtue of this Bartlett's test of sphericity is concerned, the chi-square result is 452.251 with a degree of freedom of 66. Now, with the significance has been achieved. The Bartlett's test of sphericity, as I have told you, it signifies that the null hypothesis we can reject, and that this particular correlation matrix is neither a singular matrix nor an identity matrix. You see the off-diagonal values, it doesn't have a 0. Okay, so the determinant itself is representative of that, as a result of which I told you that you can report this determinant, you can report this Kmo result, you can report this Bartlett's test of sphericity. The second group of observation or the reporting is the communality, although you need not have to report communality in your journal paper, but as far as the total variance explained is concerned, you need to report this total variance explained in the journal paper. You see how many factors have been identified: 1, 2, 3, and 4. So these 4 factors are responsible for a maximum variance explained is 71.493%. Now, these are the communalities. So basically, what is communality? Now, communality basically can be explained as the amount of variance a variable shares with all the other variables being concerned. Now, this is basically the proportion of variance explained by the common factors. Okay, so again, put into the context or put into perspective what basically communality measures. So it is the amount of variance. It is the amount of variance a variable share with all other variables concerned. Now I have got a figure of 494. Now, how I am getting this particular figure? You see, the for variable 1, the communality is 0.94. Now, the question is from where this 0.94 is coming? What is the back-end computation of this? You come to this component matrix. This is the component matrix before rotation. Okay, before rotation means before we actually check for the unidimensionality, because once we check for unidimensionality, we go for the rotated component matrix. Before I come here, I will explain the rotational factors or the rotational issues. Now, consider this component matrix. So let me bring up the calculator. Then you will understand how this communality is calculated. Now, communality basically is a summation of this particular factor score squared plus this particular factor plus this particular factor plus this particular factor. So all the squared factors. Okay, so let me do it at least to check one particular communality, and then you will understand how the communalities are computed. Sum of the squared values of the unrotated component score for each variable. So sum of squared values of the unrotated component, that is basically considered for the communality. So let me check whether the whether the exact communality value is coming for variable 1 that has been showed earlier. So within bracket, this is 0.650. So 650, we take the square value of this plus 0.167. It has a negative sign, but when I will take the square value, it will automatically get the positive sign. 167 squared plus 0.100 squared plus 0.184 squared. I close the bracket and it's 4927. That means it's almost 493, we can say. Okay, so if we can go up here, you see the communality is 494. It's almost a 493, you can say. So this is basically how the communality, from where, if you ask from where this communality score is coming, it is basically the summation of the square root, summation of the squared values for all the components for a specific variable. So for variable 2, the communality score will be square of this plus square of this plus square of this plus square of this. For a variable 3, again, the same process. So you can check each and every communality that we have got here with respect to all these, variable. The extraction of all those communalities are this. So in case of total variance explained, basically we need to identify, if we study the total variance explained with respect to or in association with the scree plot, you see the eigenvalue was fixed at 1. Okay, so the factors which are having the eigenvalue of minimum 1 are to be considered for our model. So it has stopped over here, and after that it has come down below the 1 level. So all these factors which have come down below the 1 level are not to be considered for my study, are not to be considered for my model. So my model is having a four factor structure. My model is having a four factor structure. This is the factor 1, this is factor 2, this is factor 3, and this is factor 4. And the factor 4 has almost converged on the eigenvalue 1. So it is a four factor structure. So how much variance has been explained? If you come over here, you see in the total variance explained, there are two parts. One on the left hand side, the initial eigenvalues. This is for the unrotated structure. This is for the unrotated structure. And this is for the rotated structure. Okay. So in the after the rotation, we get this scree plot result. And how many factors have been extracted? 1, 2, 3, 4, based on the eigenvalue of 1. So in this particular total variance explained, you see 1, 2, 3, 4. In the rotated, loading or the variance, 1, 2, 3, and 4. There are 4 factors only, and these 4 factors are explaining 71.493%. This is a cumulative percent of variance being explained by these 4 factors within this entire model. So this is a pretty high percentage of variance being explained, and we consider this model to be accepted as a very robust kind of a model. Now, the common method biasness that I said, it doesn't crop up here. A single factor does not explain more than 50% of the variance. If this is a case that a single factor is explaining a bulk part of the variance, invariably if it is more than 50% is explained by a single factor, then obviously there is a issue of common method variance. But here a cumulative variance of the 4 factor extracted is 71.49%. And if you see the variance of each variance explained by each of these 4 factors is 23.339, 18.070, 16.475, 13.609. Now there is a question. The question is, from where I am getting these data? What is the back-end calculation of getting these data, these rotation, the squared loadings, and these are the percentage of the variance, and how do I get this cumulative variance? Cumulative variance, you can easily understand that the individual variance summated at every row level. So 23 plus 18, it get 41, then 41 plus 16, you get 57, 57 plus 13, you get 71 point something. So cumulative is it understood. Now the issue is from where I am getting this individual variance. So again, I am bringing up the calculator over here. You see, I want to see that from where this 23.339 is coming. Okay, so let me check. See, the value over here is 2.801. This is the total value of the rotation sum of squared loadings, 2.801. If I divide this with the number of variables, that is 12, 1, 2, multiplied by, if I convert it into a percentage figure, multiplied by 100, what I am getting, 23.341. So this 23.339 is the figure that I am getting out of this calculation. So it is this particular figure divided by the number of variables converted into a percentage. I get the percentage variance of individual factor. Now the question is, from where this 2.801 is coming? So what is the input for this particular figure? If you come down to the rotated component matrix, see, when we calculated the communality, in case of a communality, we considered the component matrix. That means before the rotation. And we have calculated the communality by square of this loading, square of this loading, square of this loading, square of this loading. So it is a horizontal summation for each row. That means for each variable, the squared loading, summation of the squared loading for each of the component. In case of, if you want to compute from where this 2.801 is coming, what you have to do is, since I am considering this rotated, area, or the rotation sums of squared loadings, you have to consider the rotated component matrix. Now this will be a vertical summation across all the variable. So square of this plus square of this plus square of this plus square of this up to the square of this. So summation of square of all the loadings of component 1 across all variable will give you the figure of this one individual variable. Okay, so this you can get an idea, but I said that before just coming over here, I will just explain what the rotational issues are, or what this rotation is required for. So just allow me some time so that it can be explained. Now, as I've told you, that one of the requirement for factor analysis is unidimensionality. Say for over here, let me go back to this particular one over here. You see, in this particular rotated matrix, it is not possible in this particular format, in this particular data set, it is very difficult to identify which particular factor loading is to be retained. Say, for example, for variable 11, there is a factor loading of 0.799, and then there is a factor loading of 0.255. Both are very significant. Okay. Then for this one, variable 10, factor loading in factor 3 is 0.759, and for factor loading in factor 4 is 0.335. Now, what is basically these loadings? This is a correlation score between the variables and the factors being extracted. So the correlation score between variable 1 and factor 1 is the factor loading. Variable score correlation score between variable 1 and factor 2 is 0.115. Variables correlation score between variable 1 and factor 3 is 0.189, and so on and so forth. My point is that if you get the data in this particular format, it will be very difficult to interpret that for this variable 10 which particular factor is significant, or which in the variable 10 where should I assign this variable 10. Should I assign it into component 3 or factor 3, or should I assign it into component 4? Because both these loadings are significant for me. One is 0.7. Yes, one is higher than the other, but both are significant. I cannot discard 0.335 all of a sudden. Similarly, in this case, you see, for variable 5, it is 0.725, there is 0.237, there is 0.210. All these are significant factor loading. So the issue of multidimensionality creeps in. The problem of multidimensionality, one particular variable assigned for under different components. So I need to get rid of this for making it a perfectly interpretable model. Now, if I want to convert this anomaly into a perfectly interpretable model, I have to ensure unidimensionality so that it allows me to identify a particular variable being assigned under a particular component only. So if I go back to the data, the specification that I did not make at that particular point of time, probably you will remember that this option, I did not do anything. I did not, mention any specification. So over here, the coefficient display format, what I need to do is, number one, I need to sort it by size so that it looks nice. And the second one is suppress the small coefficient. So now it is my prerogative to fix up what correlational value I will accept for a particular, interaction between a particular variable and the factor. So if I, the rule of thumb is again zero point 0.6. So any factor loading over zero point 0.6. Now it again depends on the number of variables you are having to deal with. If the number of variable is 50 or more, then you can take it up to 7. You need to filter it out more, because more the number of variables you can take up the absolute value very high. So let us make it 6, because the number of variable that we are dealing with is not that large. We are dealing with only 12 variables. So let us make it 6 and then continue. So what we have done over here, we have done two things. One is we have just ensured that all the factor loadings are sorted by size. So it will be from a greater value to a lower value. And we have suppressed all the small coefficients. Now, while we are ticking suppress all the small coefficients, we need to assign an absolute value below which all the small coefficients will be suppressed. So any value from 0.6 and above will be retained by the model. And now let us go for continue. And now we are pressing OK. Okay. Now let us see what has happened in the rotated component. This is much easier to interpret now. Now you know that in factor 1 how many variables are included and which variables are included. In factor 2 which variables are included and how many variables are included. In factor 3 which variables and how many variables, and in factor 4 which and how. See, we started with how many? We started with 12 variables. So 4, 3, 7, 3, 7, 2. So there is basically no reduction as far as the number of variable is concerned. So all the variables was found to be very important for this particular model, and this model has churned up a 4-factor structure. So we can actually name it depending on which are the variables. You see, this is a question normally is being asked by the scholar. What is the technique of naming these components? You see, in this particular example, the ABC builder, the hypothetical example that we took, the ABC builder, before starting this particular analysis, they had an idea of 4 construct, like price consciousness and value consciousness and sale proneness and price decision index, like that. Now you may start with a very blank sheet. That means there is no preconceived dimension or component name. So what is the technique of naming or nomenclating these components or these factors? How can I name it? So naming is to be done by studying what are the variables that have been incorporated in this particular component. Which variables have been accommodated by factor 1. You study the variables, what they indicate. Okay, if you go back to the variables and if you study what they actually indicate, say what variable 1 is indicating, what variable 2 is indicating. See, both these indications are with regard to certain brands. What variable 3 is indicating, what variable 4 is indicating, because if I go here, you will find in factor 1, variable 1, 2, 3, and 4. All these 4 variables have been included. So after studying these variables, you can get certain idea what these variables are actually speaking about. Are they speaking about certain price consciousness? Are they speaking about certain brand consciousness or brand preferences or brand choice criteria? So depending on what these variables or items that you have generated, that you have created for that particular study, and the variables that have been included in this particular factor, you need to find a very suitable name for this factor. The name basically will be very indicative of what this factor actually represents with respect to your overall research objective, what you want to measure, what you intend to measure. Again, in component 2, you will find variable 7, variable 6, and variable 5. These 3 variables were included. So study these three variables, what they actually mean to say, what they actually capture, intend to capture, and based on that, find a suitable name. And in this case, if the builder finds that all these variables actually have captured or actually have represented the factors that they have considered from the very beginning, like price consciousness and value consciousness and price decision index and sale proneness, if they are matching with their preconceived ideas about certain kind of factors, they can easily use it. But you see, after the factor analysis, after the analysis is conducted, probably there can be realignment of variables across these different factors or components. Here it has become quite, you can say, predictable and almost for an ideal case: 1 2 3 4 in 1, then 5 6 7 in 2, and then 8 9 10 over 3, and 11 12. It may happen so that variable 11 and variable 3 and variable 4 are in 1. It may happen so that variable 7, variable 12, and variable 6 in component 2. So there, the study of these variables, what they intend to capture, what they intend to define, what they intend to generate, it carries a lot of meaning, and to interpret it, and deciding on a suitable name for this particular factor. Now, uh, the real issue that I was focusing on, that from a well populated matrix which had all different kind of values and probably multiple number of significant values, how we are getting this, the rotated component matrix, and what exactly is meant by this rotation. Because we have said that in factor analysis, EFA particularly, a orthogonal rotation is applied. Now, let us just, in a very simple term, let me explain without going into the very detail of this. Okay, suppose this is my x-axis and this is my y-axis. Okay, say this represents the unrotated factor 1, and this is the unrotated factor 2. Okay, unrotated factor 1 and unrotated factor 2. Say this is 0.5, this is 0.6, this is 0.7. Similarly, this is 0.5, this is 0.6, this is 0.7. And on the left hand side, this is the negative side, minus 0.5, minus 0.6, minus 0.7. This is also the negative side, minus 0.5, minus 0.6, and minus 0.7. Now, suppose a particular variable, after you have conducted the factor analysis, is lying over here. Okay, suppose this is variable 1 after the factor analysis is conducted, and another variable is lying over here. This is, say, variable 2. Now you see, this variable 1 is very close to 0.7. Say this is approximately 0.69. Okay, and this is over here on the x-axis, on factor 2, it is, say, 0.58. Okay, so both these values are extremely important, 0.69 and 0.58. These two values are very close to each other, so it will be very difficult for the researcher to conclude on which factor this particular variable to be assigned. Okay, the correlation value of variable 1 with factor 1 is 0.69. The correlation value between variable 1 and factor 2 is 0.58. Both of them are significant. Okay, similarly, in case of V2, you see, its factor 1 correlation value will be approximately, say, 0.62, and its factor 2 will be approximately, say, 0.56. Again, in these cases, both 6.2 and 5.6 are very closely and both of them are significant, as a result of which again the researcher is in a dilemma whether to assign v2 under f1 or whether to assign v2 under f2. Now comes the orthogonal rotation. See, if there is no orthogonal rotation, then the issue of uh, correlation between the factors that has been extracted will be there, because factor 1 is significantly correlated with one variable, and factor 2 is again significantly correlated with this particular variable. So that will be not a very good factor structure, or that will be not be valid factor structure. So what happens, the algorithm or the software, it goes for a rotation. It tilts these x and y axis to say a certain degree, say 45-degree tilt has taken place like this. Say it goes through the center and it goes for a tilting. Okay, now you see, once the axes are tilted by virtue of this orthogonal rotation, because orthogonal rotation we have opted simply to ensure that the unidimensionality is maintained. What is unidimensionality? One variable, one factor. That is unidimensional. One variable cannot be be assigned to two or more factors. Okay, so to maintain unidimensionality, we go for an orthogonal rotation with an objective that the factors should be uncorrelated with each other after the result or after the output. So once it is rotated, once the software rotates the this particular axis, now you see the position of v1. So this is 0.5, this is 0.6, this is zero point 0.7 probably, and this is 0.5, this is 0.6, this is zero point 0.7 in the rotated. This is the rotated factor 1, and this is rotated factor 2. Now you see v1 is over here. Say it's basically on rotated factor 1, it is close to 0.72 or something like that. But as far as factor 1 is concerned, now it is well below 0.5. Say it is coming to 0.3 or 0.2 or something like that. Now with one particular factor loading of say 0.75 and another particular factor loading of 0.2, and when you are assigning a minimum value to be suppressed as say zero point 0.6 or minimum value to be suppressed as 0.7, that means any factor loading or any correlation value between the factor and variable which is zero point 0.7 or high is to be retained by the model. Then probably it makes it sense to retain this particular variable v1 under factor 1, rather than assigning v1 to both factor 1 and factor 2 when they were in an unrotated condition. So when we talk about in factor analysis, what is basically rotation, or what is basically rotation and what is the requirement of the rotation, it is nothing but to ensure that the unidimensionality is maintained and the researcher gets an interpretable solution. Otherwise, to make interpretation about that particular factor structure would be quite impossible. So this rotation ensures that you get variables which are significantly loaded on a single factor, or in other words we can say we are eliminating the possibility of cross loading. Now the issue of cross loading is it a valid issue, or can there be cross loadings? Can there be certain kind of a structure where cross loading is acceptable or not? Tomorrow we will take a look into the cross loading issues more elaborately. There are issues of cross loading, but in case of EFA, to get a very robust kind of a valid model, normally we avoid the cross loading issues and maintain with the unidimensional structure, factor structure, which becomes easier to interpret by the scholars, by the researchers. So if we take a look into this factor analysis, our basic objective is to come over here. You know, what we actually get out of this entire factor analysis is a four factor structure. Okay, so the underlying, you know, factor structure of my observed variables, these are the variables with the help of which I have generated response. That means these are the observed variables, and these is the underlying factor structure for my observed variables. And my objective, or my responsibility rather, as a researcher now, is to name these factor structures so that it aptly describes the construct that I intend to measure. Okay, so if it is consumer perception that I intend to measure, the nomenclature should follow that particular thing. If it is perceived service quality, if it is a behavioral factor, or any other kind of measurement construct that I started to work upon with, based on that particular thing, I would go for this particular naming of the component. Naming of the component is absolutely the task of the researcher. No other will help out in this nomenclature. And this is one of the you can say a mandatory job that the nomenclature is to be issued for each and every factor. Now, a very quick look into the PSPP. Okay, so you might be interested to see, if we are not using SPSS, can PSPP give out the same kind of result? So if you go to analyze over here, you see you can populate this PSPP interface in the same way that you do in case of SPSS. So either you can import data, or you can just copy paste it from your Excel file. So over here also, if you click analyze, you will get factor analysis over here. If you scroll down, factor analysis. So all the variables, I have transferred all the variables. Initially, all the variables will be on the left hand side. So you select all these variables and transfer it into the variable box. Okay. Now you see there are two tabs over here. One is called the extractions. The second one is the rotation. So if I click this extraction, so what are the things that I need? I need a correlation matrix. I need an unrotated factor solution to see, and then a scree plot. Okay. Eigenvalues, I have fixed it to 1, and this is just go for continue. Then the rotations, I go for Varimax and check this box, display rotated solution, and the number of iteration, probably you have seen it earlier also, it's 25. It's continue, and then press OK. Okay, now you see the results. See, 71.5%. It's a four factor solution with 71.5% variance being extracted. Let us go to our SPSS finding. 71.49. So it's giving the exact result, 71.5. This is the scree plot. So you see the four factor solution has been achieved with this factor. The last factor is almost say 1.1 or something like that eigenvalue. The component matrix and the rotated component. In the rotated component matrix, however, the issue is this does not follow, this does not allow you to remove the lower values, or the values which we do not accept, because the normal SPSS is giving you a chance to suppress the lower values you select. But over here, if you are stating that I will be accepting only those values which are greater than 0.6 or greater than 0.7, then probably for component 1, variable 1, 2, 3, and 4 are accepted. For component 2, variable 5, 6, and 7 are accepted. For component 3, variable 8, 9, 10 are accepted. And for component 4, this 11 and 12. See, component wise and factor loading wise, this has resembled what we have got in SPSS. So Anyone who is interested to do this kind of statistical application but do not have access to SPSS, PSPP is a alternative which is available free of cost. It's almost an open source kind of a thing, which does all different
PSP.
PSPP. Almost, I told you, it's almost synonymous to SPSS. It's PSPP. You can download it freely and you can use it. All the statistical analysis that are to be done by SPSS can be done by this particular platform. It's PSPP.
Yes. Nutun.
So unfortunately, PSPP, yes. Unfortunately, if you don't have access to SPSS, it's not a issue, big issue. Okay. Only thing is the output, the graphical look or the layout of SPSS a little bit better compared to that of PSPP, but you require the tables. Ultimately, the SPSS tables are to be taken on the Word MS Word platform, so PSPP can be exported also, so not an issue. So this is all about the EFA. So let us stop here today. Let me complete the session tomorrow on CFA. Then we will go for a question answer session on the factor analysis as a whole. And on the third day, there is actually another software of SPSS, which is called the SPSS Modeler function. If I get a time, I will show you certain basic application of SPSS Modeler on third day. The interface is a little bit different. It looks like this. Okay, this is SPSS Modeler. This is SPSS Modeler 18 version. The advanced text mining and data mining, all the advanced analytics like predictive analytics and all those modeling like random forest, etc., can be done using this, the artificial neural networking or KNN, the nearest neighbor analysis, etc., can be done. This particular SPSS platform, it creates a chain of nodes to execute a particular operation. If I get time, I will give you a brief demonstration of IBM SPSS modeler. And